Today we're going to look at fats. Fats are the second group that we saw on your page of lipids. Fats are a combination of fatty acids and glycerol. You already know the structure of a fatty acid, so we need to look at the structure of glycerol. Glycerol is an alcohol. You can hear the ending there. And it is specifically a 3-carbon alcohol. And each carbon has an OH group on it. And again, there'll be H's down here. Every carbon has to have 4 bonds. I'm not doing all of that, it just messes up the slide. So we're just going to look at the functional group of the alcohol, which is the hydroxyl group, the OH, and add this to your list of functional groups that you need to know. All alcohols have a hydroxyl group. When you put the line out from the side that says I'm a group, I'm attached to somebody else. This is not the hydroxide ion, which can exist on its own, which has an OH and a minus written to the right at the top. So this specific structure, glycerol, is part of a fat. So let's look at how that is. Glycerol is joined to a fatty acid If you remember what a fatty acid is, it's a long chain of carbons and hydrogens. I don't have to draw the whole thing. And this is now a fat. It is no longer glycerol. It is now a fat. In fact, what we will call it is a monoglyceride. That's all one word. I'm just separating them out. It's a monoglyceride. If you want to think of it as glycerol with one fatty acid on its side, it pretty much explains what is happening here. But since glycerol has 3 OH groups, it gives glycerol the ability to combine with more than one fatty acid. And if it combines with another fatty acid, we're now going to call it a diglyceride. It can combine with a 3rd fatty acid, and then you would call it a triglyceride. So mono, di, and triglycerides are all what we call fats. Now, what we need to do is to digest the fat. Okay? And I'm taking this diglyceride and I'm going to add water to break a bond. And I would have to add twice because I have a diglyceride. And now what I have is glycerol as an individual molecule and 2 fatty acids. So you will end up with free fatty acids, free meaning F-R-E-E, in this case 2 of them, and 1 glycerol if I started with a diglyceride. Again, we're doing hydrolysis here, and hydrolysis says the addition of water to break a bond. Addition of water to break a bond. When I added the water, the bond's not going to break unless I have an enzyme to help me. The enzyme in this case will be lipase. It is the only enzyme we have for lipids. ASE ending says I am an enzyme. And you will have this in your digestive tract if you have diglycerides, triglycerides. Lipase will break that bond and release the glycerol, release the free fatty acids, so they can be absorbed. They are then small enough to be absorbed. Lipids can be absorbed rather easily because the cell membrane is lipid. Lipid can dissolve lipid. So that is the only enzyme we need in this category, versus when you look at proteins, we're going to look at least 5 or 6 enzymes. And when we look at carbohydrates, again, we have at least 4. So lipase is very simple, works on mono, di, and triglycerides to convert them to glycerol and individual fatty acids. The next group that we have on that sheet of lipids are your waxes. And waxes look a little bit like fats, but here's the big difference. They do not have glycerol. Instead of glycerol, they have a long chain alcohol. So many, many, many carbons. And they will join to a fatty acid. And form a bond. And so you have a huge molecule that resembles the bond that we saw between the fatty acid and glycerol. That's a similar bond, but what you have at this end is much longer, and we do not have any enzymes to break this down. So if you eat waxes, and you do, because lots of plants on their leaves have a waxy coating to prevent them from drying out. Apple skins, for example, are a good example. But broccoli, teeny little bit of wax covering their leaves, and you do eat it, you cannot digest it. It will just go through your digestive tract. You will not be able to break it down. But the nature of wax is to prevent water loss. We use it to wax furniture, to prevent water from damaging the furniture, or waxing your car to prevent water from damaging your car. And it is not just the water, it's what will dissolve in the water. Because if water sits on your car and there's a little pH lower than 6 and has some different pollutants in it, it can actually eat at your paint a little bit. So we put waxes on to prevent damage to the paint or damage to your furniture. Waxes, you know, can come in a bottle and you can just wipe it on, or you can get a hard wax where you really have to rub it on. The big difference is going to be how many double bonds are there in the alcohol part or in the fatty acid part. And the more double bonds you have, the more of a liquid nature it's going to be. The fewer double bonds that you have, then it's going to be one that you're really going to have to rub on, but it will hang on to the paint or the furniture a lot longer and give you more protection. Okay, we'll move on to the next group. And the next group on that list are the steroids. Okay, and one example that we've already seen of a steroid is cholesterol. But you will learn more about steroids next semester when you look at some hormones. There are many hormones that are steroids. And they have names like progesterone, testosterone, estrogen, progesterone, I may have already said that. And they are all based on this ring structure that I've just drawn here. And are they lipids? Yes, if you look at the definition of lipid, definition of a lipid is large hydrocarbons insoluble in water with many different structures. When we draw ring structures in organic chemistry, chemistry of carbons, we draw so many carbons that we don't even write them. So this would be the ring structure. It's understood at every corner, if I do not write anything in, it is carbon. So in this case, I don't have to write anything in because each of these lines, where they join, it means there's a carbon there. So what makes one steroid different than another? Well, some of them have different groups on them, like an OH group or a CH3 group, or it could have a string of carbons. And they each take a different name and have a slightly different role in the body. So you eat steroids because all cell membranes have cholesterol in them. Lots of animals have cholesterol in them, and you probably get some hormones because many animals are being fed hormones in addition to what they normally produce. So you are eating them. What happens to them in the digestive tract? They can be absorbed across your cells because your cell membranes allow them to pass through. So they can get in without being digested. Okay, they can be absorbed without being broken down. When we say they're not digested, all we're saying is they're not broken down. They're small enough to be absorbed. If they're not small enough to be absorbed, they will just go right through your digestive tract. Steroids can be absorbed. Okay, we're going to move on to a totally new group called the carbohydrates. So you should turn your page. We're going to look at a new group, new definition, and we want to distinguish each of these groups structurally. Their chemical structure is different from one another. Proteins and their amino acids are different than the lipids we just looked at. Carbohydrates are different again. The definition of a carbohydrate that I have there is a polyhydroxy aldehyde or ketone. Poly says many hydroxys. An aldehyde or ketone says I'm going to have a group that's called the carbonyl group. So we're learning more functional groups. Here's the carbonyl group. C double bond O. That's not the carboxyl group. Remember the carboxyl group. I'll draw it over here and then get rid of it because you do not have carboxyl groups. Okay? That makes it an acid. We don't have an OH on the same carbon here. So carbonyl and carboxyl are different. Carboxyl makes it an acid. Carbonyl says, okay, C double bond O. And sure, where are the OHs going to be? On other carbons. Okay? So I can have a C here with an OH on it. Fine, then I still have a carbonyl. This OH is not on the same carbon as it would have been in a carboxyl. If you have an aldehyde, you're saying the carbonyl is on the first carbon. A is the first letter of the alphabet. Aldehyde has the carbonyl group on the first carbon. For a ketone, it will never be on the first carbon. So now you have, if you think of a K is in the middle of the alphabet, when you have this double bonded O, the carbonyl, on not an end carbon, then you have a ketone. When you have it on the first, you have an aldehyde. So now let's go and put these together. And on your sheet, I have put together two carbohydrates. One is an aldehyde and one is a ketone. These are individual units of carbohydrate. Each molecule is called a monosaccharide. S-A-C-C-H-A-R-I-D-E. Mono, again, refers to one. So we're saying one saccharide, one sugar. Saccharin, which is artificial sugar, it's not a carbohydrate at all. It tastes like a sweet sugar, but they gave it its name saccharin because of the saccharide ending that we give to carbohydrates. So these are monosaccharides, one unit of carbohydrate. We count the carbons in each of these, and these are 3 carbons, so we call them trioses, T-R-I-O-S-E. So when you hear the ending OSE, that refers to a carbohydrate. 3 is tri. If I added carbons to these molecules, they're still monosaccharides, but this would now be a tetra, or a tetrose. This would be a tetrose. This would be a tetrose that's an aldehyde. This would be a tetrose that's a ketone. If I had a bigger one, I now have pentoses. Excuse me, or 5. I'm counting the carbons. And we have seen 2 pentoses. One was called ribose, and the other was called deoxyribose. Okay, we did not look at their structure at the time, but they were pentoses. And ribose has an OH on every carbon. Deoxyribose, deoxy says I'm missing an oxygen, has one less oxygen on it. So you can see where they get their names. They're very similar in structure. They're both carbohydrates. They're both pentoses. But just so you can see the difference. Simple difference. But you do not find ribose in DNA, and you do not find deoxyribose in RNA. Very specific sugars when we make them. There are some hexoses, which you know the name of. So let's look at those for a minute. There's glucose. That has 6 carbons. There's fructose. It also has 6 carbons. And another called galactose, which you may not have ever heard of, but I'll explain more what that is. But glucose is an aldehyde, fructose is a ketone, and galactose is an aldehyde. They both are polyhydroxys. They all are polyhydroxys. But the carbonyl group here is not on the end carbon. We don't have a lot of sugars with 7 carbons, so I'm just giving you the most important ones that we have in the body. The 2 pentoses we have in DNA and RNA, and these 3 hexoses that we'll see you eat a lot of. If we put 2 monosaccharides together, bond them together, not just mix them together, but bond them together, we get what's called a disaccharide. And if you join glucose with a fructose, we change its name, and that's called sucrose. That's what you eat. That's what's in your sugar bowl. That's what you call sugar that you eat. You don't say you have blood sugar of sucrose. Wonder why you don't say that. You don't say that because in the digestive process, you break the bond and you add water, an H to one side, OH to the other, and what you actually absorb will be glucose and fructose, not sucrose. So your disaccharides have to be broken down to monosaccharides to be absorbed. So we do not absorb disaccharides. They have to be broken down to individual monosaccharides to be absorbed. Okay, so what are some of the other disaccharides you eat? You eat sucrose, and you eat another that's called lactose. Well, what is lactose? Lactose is actually glucose joined to galactose. If you go back on the slides, galactose is a 6-carbon sugar. Again, you may not have heard of it because you hear of lactose. But in the digestive process, you take lactose that you get in milk, you add water and break the bond, and so what you actually absorb is glucose and galactose. Now, some babies are born without the enzyme to break this down. So if I am missing the enzyme, which is called lactase, again, here's the ASE ending, I do not have it, I can't break this down, and so glucose and galactose stick together, cannot be absorbed, and all sorts of organisms in your digestive tract start to work on these chemicals and cause inflammation, diarrhea, and a baby can be dehydrated very, very quickly. So it is something that we need to watch out for in anybody who has a new baby who has severe diarrhea. You run it to the hospital. It may be a lactase deficiency. All you do is just take them off milk that has lactose in it. And that way they'll get their nutrients from something else. Older people sometimes develop this lactase deficiency, and they too will have a problem. Some people can't even put milk in cream in their coffee. They'll get diarrhea. So if that's the case, you do not have lactase, so what you do is just eliminate lactose from your diet. Just don't ever eat it, drink it, whatever way you get it, and you won't have the problem. But again, most of us do not have that problem, but people that do have to be very, very careful. Okay, another disaccharide that we eat is called maltose. And maltose is a combination of glucose attached to another glucose. And this is called maltose. M-A-L. T-O-S-E. Tose, that's an O. Again, if I'm going to break this down, I need an enzyme to do it, and the enzyme is called maltase. Okay? So the sugar is maltose, and the enzyme is called maltase. Maltase will work to break this bond, and you will get from maltose 2 glucose molecules. You may not be familiar with maltose, but you've probably eaten it. I know you've eaten it, but may not have eaten it in the form of maltose. But if you've eaten malted milk balls, you can taste the flavor of that sugar is a little different than table sugar, different than your sucrose. They used to add it to milkshakes, and we called them malted milkshakes. So you do get it, and I'll explain other ways that you get it. Okay, so we eat monosaccharides, we eat disaccharides, plenty of disaccharides. We also eat what we call polysaccharides. And polysaccharides say, okay, I have many, many, many molecules linked together to give me a big molecule. And there are only 3 polysaccharides that I'm requiring you to know. One is called glycogen, and the next 2 are from plants, and they are called starch and cellulose. They all are made up of glucose molecules over and over and over and over and over again. Just linked together over and over and over and over and over again. That's why we call them polysaccharides. But they're all made up of glucose units. So let's look and see what's the difference. And do they taste different? Do we digest them differently? What is the difference? Well, let's look at glycogen first. This is made in animals, You have it in you. It's very important. Your liver is loaded with it. Your muscles are loaded with it. And if I illustrate glucose molecules as a circle, glycogen has many, 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 many glucose molecules linked together, and they branch. And so this is what glycogen would look like. Each of these circles represents a glucose molecule. Now, if I'm going to break down this glycogen, I have to get it down to monosaccharides to be absorbed. So I need to break every single one of these bonds to absorb the glucose molecules. And we start this process with an enzyme called amylase. ASE, amylase. And you have this in your mouth, and you'll have it a second time when you get into your small intestine. So this is one of the only enzymes that we have 2 times. In the course of evolution, I guess everybody ate fast. And so they didn't leave the food in their mouth long enough to be broken down. And those of us who have the second amylase later on were able to get better utilization out of our food and were selected for and survived. So amylase we're going to get twice. Okay, so amylase works on glycogen, and amylase also works on starch. And starch, keep in mind, comes from plants. And starch is glucose molecules linked the same way as we saw in glycogen. But if I said to you that hamburger and the roll on a hamburger tastes the same, you'd say I was crazy. Because they don't. They have a different texture. But they're actually made up of glucose molecules linked together and with some branches. But in starch, the glucose molecules have longer lengths, meaning that there's not as much branching, and the branches are longer. So fewer branches and longer branches gives you an entirely different taste between the hamburger and the roll. Different texture, but it's the same stuff that you're actually eating. So if I'm going to break down starch, I need amylase, and amylase will break down the bonds. Okay, it starts by breaking at the branches and then continuing to break it down. If you want to get a different flavor from starch, you can eat a piece of Wonder Bread, white bread, and leave it in your mouth. Don't swallow, just leave it in your mouth. Let it mix with your saliva. And in a few minutes, it will taste sweeter and sweeter and sweeter because you're going to be releasing the sugars. Especially what you'll be releasing is maltose, 2 glucose molecules linked together. And so you'll get that flavor very, very quickly. Now, let's look at this. Cellulose, we also said, came from plants. Cellulose is also, not spelling it correctly here, hold on. It's also made up of glucose molecules. But the glucose molecules are linked differently. Okay? And they're long, 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 long chains with very little branching. Cellulose is in celery. You know how stringy celery is. We call these fibers. These are not like what we saw in the fibers in connective tissue. Those fibers were protein. In connective tissue, when we looked at collagen and elastin and reticular fibers, you can actually digest those. These are cellulose fibers made up of glucose. And even though it's glucose, it's linked differently, and we do not have enzymes to break these bonds. So these will stay as fibers in our digestive tract. And they add what we call bulk. And they stimulate our digestive tract to move and push the material along. So it is useful to us, but we do not get any calories from it. And we cannot absorb the cellulose fibers. We cannot break them down, so we can't absorb the glucose that's contained in them. There are some organisms that can, and we're looking at finding a way to break it down easily, because there are lots of third world countries that would be able to thrive if they had more calories. And if we could break down the cellulose and give them carbohydrates that would be calories for them, it might be beneficial. Okay, so for us, we need to have monosaccharides to be absorbed. And if they're not in that form, we need to break them down, or the other word for that is digest them, so that we can use them. Next class, we will go through the digestive tract and follow what happens in the mouth, the esophagus, stomach, intestines, to each of these foods. This is why you need to know what they are. Then we'll pour in the enzymes in each place and see what you end up with to be absorbed. And I will see you Monday. As you listen to this, if you have questions, please write them down. We'll go over them when we talk on Monday. Thank you.